So today we're going to do exactly the same thing, but this time we're going to be looking for complex zeros, rational and irrational, or imaginary as well. Okay, so that's what this is about. Let me put the file in the chat before I keep going. And I hit record. We're good. We're on a roll. Complex zeros. Bam. Okay. All right, look at this lovely page of definition. So a variable in the complex number system is referred to as a complex variable. A complex polynomial function f of degree n is a function of the form. And again, here is our standard form of a polynomial. You start with the highest power and you end with the constant. So we've seen this form before, where a sub n minus 1 to the constant, they are complex numbers. And of course, the leading coefficient cannot be 0. And your exponents are non-negative integers, and x is a complex variable. As before, a sub n is still your leading coefficient, and a complex number r is called a complex zero of f if f of r equals 0. So this means that we're going to be finding zeros again. We're going to be finding values to break down these polynomials. And remember, it's called a zero for a reason, because if you plug it into the function, it should zero out the function. And this will work with complex zeros. Okay, so we have learned that some quadratic equations have complex solutions, imaginary, but that in the complex number system, every quadratic equation has a solution, either real or complex. This was proved by Carl Jones Gauss when he was 22 years old, which is known as the fundamental theorem of algebra. So if you guys don't know anything about Gauss, you should look him up. He's actually really important and the reason we're able to do a lot of things in math. This guy was making up his own theorems when he was in kindergarten. So, and the fundamental theorem of algebra, I think, was created in 1797, something like that. So definitely an interesting read. Look him up. Okay. So with that being said, the fundamental theorem of algebra states that every complex polynomial function of a degree greater than or equal to 1 has at least one complex zero. So if you have a degree of a polynomial greater than 1 and we solve for the zeros, then at least one of them should be a complex zero. Okay, and then the theorem, every complex polynomial function of degree greater than or equal to 1 can be factored into n linear factors of the form. So again, this is what we were doing on Monday. We were taking polynomial functions and breaking them down into factored form. So you'd have a sub n times x minus r1, r2, all the way to the final factor after we break down the polynomial. So what we're seeing is nothing new, but just more definition behind it. Okay, where a sub n, r sub 1, r sub n are complex numbers, and that is every complex polynomial function of degree n or greater than or equal to 1 has exactly n complex zeros, some of which may repeat. Blah. Okay. So with all that being said, like, we're going to do the same thing that we did Monday, but this time we are actually going to look for complex zeros. We're going to look for real zeros and complex zeros, and we're still going to break down polynomial functions by synthetic division using the potential zeros and putting them into factored form. As well, we're going to be given zeros, we're going to put them into their factored form, and then distribute them out to give us the standard form of a polynomial. So we're going to be making polynomials from the ground up, and we're also going to be breaking polynomials down. So all the fun you can handle today. All right. So first up is the conjugate pairs theorem. Let f of x be a polynomial function whose coefficients are real numbers. if R equals A plus BI is a 0, then its complex conjugate, A minus BI, is also a 0 of F. So if you're looking for complex zeros, just know that they will always have a conjugate. So if I was given a 0 of A minus the square root of B, then this means that I would get a conjugate 0 of A plus the square root of B. So if we're ever given a complex 0, just know that it will have a conjugate. Okay. And then corollary, a polynomial function of odd degree with real coefficients has at least one real 0. So if we're given an odd degree polynomial, we know that at least one 0 will be a real 0 and the rest are complex. Okay. So the next page, we're just going to try out conjugate pairs theorem. We're going to be given zeros and told to find the remaining ones. Okay, so first up, a polynomial function of degree 5 whose coefficients are real numbers has the zeros 1, 5i, and 1 plus I. Find the remaining zeros. Okay, so which of these zeros given are complex? Nobody?
Is it the ones with I?
Yeah, those are going to be your complex zeros. 5i and 1 plus I, which means if they're complex, they have a conjugate. So what are the remaining zeros?
1/5 I and then 1 minus I.
So it's going to be 1 minus I, but then you can just, since it's a positive 5i, its conjugate is going to be negative 5i. And now, how many zeros do I have?
The 5.
5. What was the degree of the polynomial?
5.
5. So that matches up. So that's how conjugate pairs theorem works. You look for the complex zeros and you find their conjugate pair. Okay, try it again. A polynomial function of degree 4 whose coefficients are real numbers has the zeros I and 1 plus I. Which means that these are definitely complex. So what would the remaining zeros be?
Negative I, 1 minus I.
That's it. And now we have 4 zeros and our degree was 4. Okay. Next, a polynomial function of degree 6 whose coefficients are real numbers has the zeros 2, 2 plus I, negative 3 minus I, and 0. There we go. Right. It doesn't want to write. All right. So we have 2, 2 plus I, negative 3 minus I, and 0. What are my remaining zeros?
Two minus I, negative 3 plus I, and
that's it.
That should be it. Yeah, there's 6.
Good, because now we have 6 zeros and our degree was 6. Okay, and that's conjugate pairs theorem. So if you're given a complex 0, then you should know its conjugate pair. Any questions on that page?
Hold on, what did you say right now about conjugate pairs?
So with conjugate pairs, if you're given a complex 0, then you should automatically know that it has a pair, a conjugate pair.
Oh, okay. Yeah. Cool.
All right. Okay, cool. With now, find a polynomial function of degree 4 whose coefficients are real numbers that has the zeros 1, 1, and -4 plus I. All right. So on this example is where we're going to build the polynomial function from the given zeros. So we're going to take the zeros, put them into a linear form, and then distribute everything to find the standard form of a polynomial. But to begin with, let's find our remaining zeros. They give me 1, 1, and -4 plus I. What's my missing zero?
-4 minus I.
That's it. -4 minus I. Okay, so now what we're going to do is put this into factored form. So I'll say factored form. How can I rewrite my 0 of 1 as a linear factor? Remember, we're going for this form, or x minus r1, x minus r2, till we get to the last 0. So how would we write 1?
It's this x minus 1.
That's it, x minus 1, which means now you have to write this one. As x minus 1. And now we have to write the last two using the same method. So this is going to be x minus, and I'm going to put these in parentheses, -4 plus I, and x minus -4 minus I. All right, so we have just taken our zeros and put them into a factored format, into a linear factored format. Any questions so far? Okay.
No, I think I see it.
All right. So what we're going to do now is distribute everything. But before we do, we're going to clean up the ugly parts, which are these two on the right side. So let's go ahead and do that first. I'm going to leave this as x minus 1 times x minus 1. And then I'm going to go ahead and distribute these negatives on both of them. So when I do that, I get x plus 4 minus I, and I get x plus 4 plus I. Okay, so now we want to distribute everything, but before I do, I'm going to use something called the associative property for addition. So this x plus 4 minus I, I'm just going to rewrite it as x plus 4 together minus I. And the same thing over here. X plus 4 plus I. The reason I do this is it's going to make our distribution process a lot nicer to look at. Okay, And what I just did here was I said, right, Carl? Associative?
E.
Yeah. Is that I took A plus parentheses B plus C, and all I did was rewrite it as parentheses A plus B plus C. Haven't done anything wrong, just rewrote it.
Yeah. Associative changes who's talking to who. Commutative changes who's standing next to who. It's the way I would think about it.
Gotcha. Okay. So now everything's nice and neat. So now we're going to distribute everything. So I'll start with the left side, the x minus 1s. Those are easy. If I distribute these or FOIL these, I'll get x squared minus 2x plus 1. Okay. And now I'm going to put a bracket here just to be neat. And now we're going to do this FOIL process. X plus 4 times x plus 4 is going to give me x plus 4 squared. And then x plus 4 times I gives me x plus 4 times I. And then negative I times x plus 4 gives me negative x plus 4I. And then negative I times I gives me negative I squared. Close bracket. All right. Any questions so far?
Is it always going to be in that kind of general format for the last part?
Like what I have in the brackets?
Yeah.
Yes.
Except for, okay. Except for
Yes.
the different numbers. Cool. Be a lot easier.
All right. Okay. So now we clean up more. I'm going to leave the first set of parentheses alone. And now we have to expand. X plus 4 squared is x plus 4 times x plus 4. What's going to happen to your x plus 4 i's?
Would they cancel out to form 1?
They will just cancel. Because they are the same term, just opposite signs. Okay. And then last, what is I squared? First off, what is the value of I?
-1.
The square root of -1, right?
Yes.
Then what would I squared be?
-1.
-1. And then what would negative I squared be?
Just 1?
Just 1. There you go. So that means now you just get x plus 4 times x plus 4 plus 1. All good? Okay. And of course, more distributing to follow. Leave this alone. Distribute your x plus 4s. That should give you x squared plus 8x plus 16 plus 1. Still leave this alone. And now clean that up, and we should have x squared plus 8x plus 17. Okay. Still not done though. all we did so far was just get rid of the complex values. We got rid of the imaginary numbers. So now we have to distribute this final form. All right. Now distribute, and we're going to get x to the fourth plus 8x cubed plus 17x squared. So I'm going boom, boom, boom. And then I'm going to go with the -2 now. And go boom, boom, and boom. So negative 2x cubed minus 16x squared minus 34x. And then last is the 1. Boom, boom, boom. Plus x squared plus 8x plus 17. And now all of it has been distributed out. And just combine like terms. So here, x to the fourth, no other x to the fourth, so that's coming down. And then next is cubes, 8x cubed, negative 2x cubed. This would give us 6x cubed. And then squared, 17, 16, and x, 1x squared, that's 17, 16, 1, 1, so we get 2x squared. And then last is x's, negative 34 plus 8, negative 26x, plus your constant. And there it is, guys. So, given the zeros of a polynomial function, you can put them back into a linear factored form and find the original polynomial in standard form by distributing everything out and getting rid of those complex values. I guess I could put, what is it? F of x equals. I think my MATLAB puts an A in front of all of it too, but you don't have to type that. I think it has it set up with the A in front. Okay. Any questions on that one? It's a lot of distributing, right? All right, then. Oh, another little theorem down below. Every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. So again, another theorem stating everything we've learned so far. We know that we can break down polynomial functions by synthetic division and potential zeros to put it into a form of linear factors. And some of those linear factors could be irreducible quadratic factors. Or I shouldn't say linear, but some of those factors could be irreducible quadratic factors. Okay. So just putting more definition behind everything we've been doing. All right. Woohoo. You want to do one, Carl?
Yeah.
All right.
I was cleaning up the last one we were working on, but that works. I can show them the way I do the big gross thing. You want me to do it on those notes? You want to just send me the link real quick?
Yeah, I'll send you the link. And share. And that. And that.
Let me turn on my lights in my room real quick.
Fun
Sitting here in the
Carl.
dark like a vampire.
We are vampires.
Caveman. Or both.
There you go. I sent you the link.
Vampire caveman?
Vampire caveman.
I know for me, I have a habit of just like turning my lights off like that too. Now I have to get like a backlit keyboard so I can like actually see it.
This stuff's no good for you. It's bad for your eyesight.
It's not.
At least that's what the old people say. All right, let's see here.
I have a red lit keyboard.
Heck yeah. All right, let's share my screen. Share my screen. Here we go, math files. And share. All right, you guys can see the whole thing?
Yep.
Cool. Let's get that out of the way. Oh, I gotta go to the right book. That's right.
There you go. 5/7/2021. Bam.
Cool. Oh boy. All right, cool. So get a pen, draw. It's a little big. Okay, so where's the thing that lets me scroll? All right, so we want to find the complex zeros of this polynomial, which we're going to do by factoring it. So the first thing we want to take note of is our degree, right? So our degree here is 4. That tells you that right there, your leading coefficient, right? And then we want to do the same thing we've done previously. We want to find our values of P and our values of Q. And this looks like we have plus or minus. This is 18. So this is going to be 1, 3, 6, 9, and 18.
2.
Right? 2. Oh, yeah, 2. Duh. This pen is still kind of big. 1, 2, 3, 6, 9, 18. And then our leading term is 3. So that's just 1 and 3 because 3 is a prime number, right? So this will give us plus or minus 1, 2, 3, 6, 9, 18. And then we'll also get 1/3, 2/3. 3 divided 3 is 1, 6 divided 3 is 2, 9 divided 3 is 3, 18 divided 3 is 6, which are already all in there. So these are all of our potential zeros, plus or minus all them things. So we're going to test those out using synthetic division. So we have 3, 5, 25, 45, and then negative 18. Nothing to skip. Which one do we want to try first? Why don't we try? Let's try -1. Why not? Let's see what we get. Maybe it'll work. Maybe it won't. So we get 3 for free. So -1 times 3 is -3. That gives us 2. -1 times 2 is -2. That gives us, what is that? 23. Negative 1 times 23 is negative 23. That gives us, what is that, 42? No, 22. 22. That's not going to work, is it? Nope. Okay. Well, the wonders
Negative 1's out of here.
Negative 1 is out of here. The beauty of digital is I don't have to spend a whole bunch of time erasing my paper now. Why don't we try... 2 is going to get too big. Why don't we try negative 2? We get negative 6. This is negative 1. And then we'll get 2. This is 27. Possibly looking good, maybe? Yeah, I think that'll do it. So negative 2 times 27 is negative 54. And then this gives us negative 9. That'll do it. 18. So we have 1, 0. So let's rewrite this here. We will get x plus 2 times 3x to the, we started at 4, 3 minus x squared plus 27x minus 9. All right, this is factorable right here. I can tell by looking at it because I have tons of experience, but you should always try it. You should always try it as soon as you get 4 terms. Just see if you can do a factor by grouping. The worst that'll happen is you'll save yourself a lot of time. Or maybe you'll have to spend a little bit of time, I should say. So if we rewrite this as 3x cubed minus x squared times plus 27, I put the sign out there in here with it instead of writing it in the middle. Sometimes you can help yourself out by putting whatever sign is between the 2 groups, between the 2 sets of parentheses. That's something I've heard before, but that like works out sometimes. Try it out, see how you feel about it. I just do it like this. So if we pull out here an x squared, that leaves us 3x minus 1. And if I pull out a 9, specifically a plus 9, then we get 3x minus 1. Look at that. So this factors to x squared plus 9 times 3x minus 1. So our whole factorization then gives us x plus 2 times 3x minus 1 times x squared plus 9. All right. So what was this, an f of x? What did it start as? F of x.
Yeah,
okay.
F of x.
So we'll say this equals f of x. F of x. Cool. So then now we want to try to find our complex zeros, right? So looking at these, which of these 3 could potentially give us complex zeros?
X squared plus 9.
The x squared plus 9, right? So let's go ahead and we can check the other 2, but I mean, you can kind of tell by looking, you won't get that. So let's do x squared plus 9 equals 0. So we'll get x squared is equal to negative 9. We take the square root on both sides. So we will get x is equal to I times the square root of 9, which is then equal to plus or minus 3 times I. So our complex zeros then, since that is what, if I'm not mistaken, that's what this asks us, find the complex zeros. Our complex zeros are 3i and negative 3i. And that's that. Any questions?
It may want them to write it in factored form with the actual complex zeros.
Gotcha. So let's...
I know it was being picky last semester with that.
All right, that's not a problem. Let's go ahead and write it out then. So if we have these 2 in here like this, one thing that you'll notice or that you should remember, this helps me sort of make sense of these because sometimes you can get lost trying to write the complex zeros the right way. A complex zero has this form. Complex, or really I should say a complex number has this form, right? It is a plus b times I, right? Where this is the real number and this is the imaginary number, right? So if we take a look over here at this 3i and this negative 3r, we don't have the real one in there, but what can help you make sense of these sometimes when you write this all the way out, at least it does for me occasionally, is to write it like this. X, in this case, it will be minus 0 plus 3i, and then x minus 0 minus 3i. Maybe the 0 isn't necessary for you. Maybe it is. I know it's helped me avoid mistakes before. So if this makes more sense to you to do it this way, do it this way. If it doesn't, take the 0 out. It doesn't change anything. So then this will be equal to x plus 2 times 3x minus 1 times x, distribute your negative, negative 3i, x, distribute your negative, plus 3i. And that is the fully factored form.
Woohoo, yeah, it does. I'm checking right now, and it does make him put it with like you have it.
With the 0 and stuff?
Yeah.
Yeah. This is something that's like...
Can you circle which one it wants?
The final writing he has there, the blue one.
So
Yeah.
this one right here?
Yeah,
is the
exactly.
right one?
That one.
Okay.
Thank you.
Yeah. This is one of those persnickerty math things where if you want to be very technical, I know in 410, my math lab, when we were doing complex numbers, if they were 420, whichever one that class was, if they weren't including the 0 plus the imaginary part, it was telling them wrong. So, but yeah, that's
Terrible.
it. Any other questions? I'll take that as a no.
Take the last one if you want it.
Sure, let's knock it out. Okay. Test the given 0 by synthetic division to find the remaining zeros of the function. Okay, that's not so bad. All right, so remember we have to write in our missing spots. We don't have any. So let's bring our coefficients down. 5, 5, 20, and negative 12. Really, let me do this. So when you do synthetic division with complex numbers, give yourself space because sometimes the arithmetic can get a little roomy. All right, so we want to start with negative 2i. We get 2 for free. So then this gives us 2 times negative 2i. So this is 4 negative 4i. Guys, I'm not going to lie. I forgot how to multiply real against imaginary for a second. Negative 4i. So then we'll get 5 minus 4i. Negative 2i times this will be, oh boy.
You may want to write it out with side work.
Yeah, I'm going to have to do this as sidewalk.
Yeah.
Sometimes you can fit it in there, but we won't do that because that's really complicated. So we'll get negative 2i times the quantity 5, or times the complex number 4 minus 4i. So that is negative 10i plus 8 times I squared. So then this is negative 10i plus 8 times negative 1. So this is negative 8 minus 10i is our number. So then we're going to put that up there, negative 8 minus 10i, which gives us negative 3 minus 10i. All right. So then we have to do this again. Negative 2i times negative 3 minus 10i. If you haven't caught the pattern already, this I squared is just going to switch the sign on the real part of the complex number every time. So we're going to get here negative 6 positive 6, just kidding, I plus 20 I squared. So this would be negative 20 plus 6I. All right, negative 20 plus 6I. Look at that. It works out perfectly. This will give us back just 6I. And then our last one is negative 2I times 6I, which is negative 12I squared, which is just 12. And look at that. We get our 0. Okay, gross. So we want to rewrite this as x plus 2I times, we went down one linear factor. If I can remember to write my coefficient, 2x cubed minus plus 5 minus 4I x squared, I think is how you do that. Yeah.
Yep.
Plus negative 3 minus 10I x plus 6I.
It looks fantastic.
Man, that is so gross. Okay, so now we want to try to simplify this down. Wow, okay, this is really gross. I 2x cubed plus 5x squared. You can't do that. You cannot do that. Never mind.
So
I was just running on autopilot for a second. Let me see. What
you're going to throw it back into synthetic because you were given a complex 0.
Yeah. So we're going to try our other complex. Yeah.
What is the remaining complex 0, anybody?
Three I.
Well, it's negative 2I, so then it would be
just 2I.
2I. There you go.
2I. Yeah.
So we're going to do this again with 2I. That is right. Gross. Give myself lots of room here. We have 2, 5 minus 4I, negative 3 minus 10I, and then 6I. Okay, wait, can I just do this right? No. Okay, well, never mind. It won't let me draw around that. Whatever. We'll have to go back to just this then. Okay, so we get our 2 for free. So this is for I. This gives us, I don't know if that's how that works. Yeah, it does. Yeah, you just get 5 back. Because again, this is a plus 0 out front. So we get back 5. So then this is just 10I. So we get negative 3. And then this would be negative 6I, which gives us 0. So now we get, rewriting this down, we would get x plus 2I, x minus 2I, and then we've reduced by another linear factor, 2x squared plus 5x minus 3. And then can we factor this one? I think we cannot. Wait, maybe. Let's see.
We hope we can.
Let's see. We have 2x squared plus, let me erase this. Do it in a different color. Is that okay? So we have 2x squared plus 5x minus 3. Our factors are 2 and 1 and 3 and 1. So we have to take 2x and x because 2 is prime. Is there any combination we can put together to get negative 3 out of this and plus 5x? Yes, there is. We can do plus 3 minus 1, and that would give us 2x squared plus 6x minus x gives us 5x, and then we get negative 3 on the ends. There you go. This is the guess and check method, like drawn out, if no one's ever seen that. Usually you'll have like a longer list of factors you can guess and check through. So then this becomes equal to x plus 2i times x minus 2i times 2x minus 1 times x plus 3. Now that's totally factored. What does test the given to find the remaining zeros? Okay, so then we just want to list what our zeros are. So our complete list of zeros is as follows. We've got negative 2i, 2i. 2x minus 1 is 1/2 as a 0, and negative 3 is our other 0. And then each of these, each with multiplicity of 1. All right. Was that everything it asked for? Yeah. Okay. Gross. Sometimes you get to watch an upper division math student have to relearn basic algebra on the fly. And maybe that's fun. I don't know. Any other questions on this while we're here? I'm gonna take that as a no. All right.
Oh yeah, they're weird. Yeah. Okay. Everybody good?
Man, I hope so.
They're all quiet. That was 5.7. So again, not much different than the last class. Just we use complex zeros and real zeros to build a polynomial function. And then you just saw that you can break down a polynomial by using imaginaries in synthetic division. If
I
that
actually do
didn't,
have one question. I'm sorry about that.
go ahead.
What if the remainder is not a 0 after all that? Then what?
Then you might want to check your work.
Okay. So there will not be any instances to where even if we do recheck our work and it still gives us the same remainder, there's no such instances in the particular problems?
No, there shouldn't be. Like,
Okay.
just go ahead and double check. But if it did happen and you double check your work multiple times, then there would be no answer to that. But I don't think I'm that cruel.
Oh, okay.
Yeah. I'm gonna say if it starts by telling you it's a 0, you should definitely get a 0 after synthetic division. And if you don't, then maybe it's a problem. Like Robert said, if you check it a whole bunch of times and it's still not coming out right, it could potentially be like an error in the textbook or an error in the system that generates the problems, but those are pretty rare. Usually it's just an algebra error.
Understood. Thank you.
Sweet.